So today is usually most students' favorite day in calculus because we're going to go over some basic differentiation theorems. And so I want to take a second to remind you what a theorem really is. So the definition of a theorem is a provable proposition or formula, a proposition or formula in mathematics or logic that is provable from a set of axioms and basic assumptions. So that's a great dictionary definition. The second one is mine. It's basically a tool used by mathematicians to save time since it's the same work that has been done a lot already. Okay, so the idea is we define these derivatives in terms of limits, but we don't always want to go back and work through the limit every time. Working through these, hopefully you've seen that you've done the same work over and over and over again. So what we can do is we can develop a shortcut as long as we can justify how to use that shortcut. The big thing is, though, you need to remember the ideas, not just how to push symbols around a page, okay? You can only use the theorems if you're sure that they're going to work, that you're sure that you can use them. Don't just try things and hope for the best. Make sure that they work. So our first big theorem we're going to learn is the constant theorem, which says that the derivative of a constant function is 0. That is, if you have any real number c, then the derivative of that constant is going to equal 0. And so let's think about what this really means. So here we have the graph of a typical constant function y equals c, and the derivative, remember, is just a shortcut word for saying, well, what's the slope of this function? And so if you look at this line, you ask yourself, well, what's the slope of this line? Well, the slope is always going to be 0. So that's what this theorem says. Take a constant, ask the question, what is the slope of this constant line? 0. Now, the world has a long history of thinking things are good ideas and finding out that they're actually wrong. So in math, what we try to do is we also try to do things very carefully. So let's carefully look through our limits and see why, according to our limit definition, the slope will always be 0. So we start by saying let f of x equals c be a constant function, and then we need to set up our limit definition. So here we have our familiar limit definition with our good friend the difference quotient inside that approximates the slope a little bit of ways from a point that we're concerned with. And the key here is that in our function doesn't care if it's f of x plus delta x or an f of x. No matter what you put into our function, we're always going to get out the same constant c. So that really helps in our difference quotient to tell us that what our rise is going to be c minus c. So since our function has 0 rise overall, this means we're taking the slope as we get closer and closer to our point of all 0 slopes all the time. So this means our slope all the time is going to be 0. So before we get on to our next idea, the power theorem, we need to review a little bit how to multiply things out. So x plus y is just going to equal x plus y. Nothing too fancy going on. Then if you take x plus y and square it, well, you get x squared plus 2xy plus y squared. You've probably seen this pattern a fair amount in algebra. Perhaps you had an algebra teacher who made you multiply out x plus y cubed by hand, so you got to distribute twice, collect terms. This equal sign is basically standing in for a bit of work to get x cubed plus 3x squared y plus 3xy squared plus y cubed. When you do it to the 4th power, you get this neat little pattern here. Please ignore the extra plus sign. And if you kept doing it, what you would get is you'd get a neat pattern, but it's kind of hard to see. It's a little messy in here. So instead what we do is we look and we think, well, what are the coefficients? My numbers in front of my x's and y's here. Well, I had a 1 and a 1. In the next line, well, I've got a 1 in front of the x squared and 1 in front of the y squareds. So I've got 1's out here. And then I have myself a nice little 2 in the middle. Next, I get the 1 in front of my x cubed. I get a 3x squared y, a 3xy squared, and finally a 1. And in the last line, I get 1, a 4, a 6, a 4, and finally a 1. And if you kept doing this, what would happen would be a neat little pattern. It's called Pascal's triangle. So what's neat is that along the triangles, the diagonal parts here, we always get 1's. And then to get the middle numbers, what we need to do is we need to take this 1, add it to the one next to it, and we get 2. We take 1 and we add it to 2, and we get 3. 2 plus 1 also makes 3. 1 and 3 makes 4. 3 and 3 makes 6. 3 and 1 make 4 again. And what you can even do is you can even keep continuing this pattern. So we're going to get a 1 along the diagonal, 5, 10, 10, 5, and finally a 1. And this pattern just keeps going and going and going. It's been proven it keeps going. Now this is important though because it's going to help us with the following idea. So let's look at this monster here. Suppose for some reason you decided that you wanted to multiply out the quantity x plus delta x to the n. Well, what are you going to end up with? Well, you're going to end up with a lot of stuff, but what's important is that the first term is going to be x to the n. The last term will be delta x to the n because we've got 1's in front of our coefficients here. And all the terms in the middle, what they're going to have is they're going to have delta x's in them. The numbers out front are going to be varying numbers. They're going to keep getting bigger, but they're going to be non-zero, and we're going to have lots of delta x's. Now the reason we're concerned with this is because the power theorem has x's raised to powers. So we've already computed a few powers functions before. We've computed the derivative of x is 1. The derivative of x squared becomes 2x. The derivative of x cubed becomes 3x squared. And so the question is if you kept doing this, would you notice a pattern? Is there some sort of pattern here that says, well, x just becomes 1. You know, I see this 2 here, and I get that 2 over there. I get a 3 here, and I get 3 there. Here, the squared changed down and became a 1. 3 became a 2. Is there some sort of pattern here? And in fact there is, and we call it the power theorem. So next what we have is we have called the power theorem. So it says if n is a real number, that is if your exponent's a real number, then the function f of x equals x to the n is differentiable, and we can find the derivative of x to the n is going to be equal to n times x to the n minus 1, as long as this thing makes sense. So for f to be differentiable at 0, n must be a number such that x to the n minus 1 is defined on the interval containing 0, okay? So as long as this thing makes sense when you compute it, it is going to be the derivative. We'll talk more about this in a little bit. But first, let's go through and look at the proof of this. So if we try to prove this using the limit definition, what we do is we get the basic setup with our difference quotient right here. Not too bad to look at. The problem is that when we try to multiply this thing out, we're going to get that huge mess we saw previously. But as always, the key here is to simply not panic, okay? The key thing to notice is that, well, we just need to start canceling and see what happens. We have an x to the n up front, we have a minus x to the n in the back, so those are going to cancel, and this gets a little easier to look at. Next, if we look at this, the key to this whole limit problem is we can't substitute delta x right away because we divide by 0. So we need to figure out a way to cancel it. And well, if we look at all our terms, this first term has a delta x in it. And then if you looked really carefully, you'd get a whole bunch of terms, but you have delta x at least to the second power. Maybe it's to the third, fourth, fifth, whatever, higher and higher. Like this last term has delta x to the n. So there's lots of delta x's there, one in each term, so we can go ahead and factor one out. So here we've gone and factored them out, and the key here is that these extra terms in the end that had delta x to the 2 or higher still have a delta x term in there. But now that we've factored this delta x out in front, we can go ahead and cancel it with 1 in the denominator to get something pretty nice. Because what this is going to equal then will just be n times x to the n minus first plus a whole bunch of zeros. Because each term here contains a delta x, so they're all going to go away. So what we have here is we have our nice little power rule here. It says that if we take the derivative, we need to bring our exponent down in front and subtract 1 from the current exponent. And we're good to go. So now let's see how this thing works with some examples. So let's try to find the derivative with respect to x of the function g of x equals x to the 1/5. So we go ahead and we set this up that we're going to take the derivative. And now the key is that in this case, n, our exponent, is 1/5. So what we need to do is we need to bring this down in front. So we end up with 1/5 x to the 1/5 power minus 1. Here's the place where we always want to be careful with our arithmetic. When you remember that 1/5 minus 1 is going to be -4/5. And so this right here is our answer. Now, an important thing to note is that our original function was defined at 0. I can put 0 in there. The fifth root of 0 is 0. But it doesn't have a slope here at 0. Okay, the slope here ends up probably being a vertical tangent line. The graph of the 1/5 power looks something like that. And if I draw on my axes, so what here is we have a vertical tangent line, so that's why we can't put 0 into our derivative. Alright, let's try another one. So let's look at the function 1 over x cubed. Now at first glance you might think to yourself, this doesn't really fit the pattern. Our pattern, we need x to the n, but what we can do is we can always try to rewrite things algebraically so they fit the pattern. So here the key feature is to remember that 1 over x cubed, that's a terrible cubed, means the exact same thing as x to the negative third, and now it fits the pattern. So in this case, our exponent in this case will be n equals negative 3. So now what we can do is we can try to take the derivative of this function, 1 over x cubed, which means we want to take the derivative of the function x to the negative 3, which means we're going to move the negative 3 down, and then always write this step out. Don't try to do it really quick in your head. Negative 3 minus 1, which simplifies down to negative 3x to the negative fourth. This is a step that many people just go quickly, they write too fast, they're going to end up with a negative 2 here instead of a negative 4, so we just want to be careful, show our work, check our steps, that this is indeed the right answer. Let's look at one more example before we move on. So our last example is k of x equals 1 over x. And hopefully, what you're thinking to yourself is, oh, this isn't so bad. 1 over x, I just have to rewrite it so that it fits my pattern nicely. So the derivative of this is going to be the derivative of x to the negative first. And let's see, I bring the negative 1 down, I take x, minus 1, minus 1. And I clean it up a little bit, negative x to the negative second. All done, not a big deal. The key feature, of course, is always this rewriting step. Remembering that x with no power is really an x to the first secretly, and then lots of times we got to bring stuff up from the denominator into the numerator here. So next we have the constant multiple theorem, and the reason this theorem is really neat is because it allows us to figure out derivatives when we don't even actually know the function, but we can still start to manipulate and start to figure out what the derivative is. So this theorem says that grab yourself function that's differentiable and see any old real number. Then if we take the product c times f, that's going to be differentiable, and we can find the derivative of c times f of x by taking c times the derivative of f. Now this is really abstract. I don't know what my function is, f, but basically what I can do is I can take this constant and pull it out of the derivative function. Okay, so the way you want to remember this is that the derivative of a constant times a function is that constant times the derivative of the function. So let's take a look at how this thing works with some examples. So we're going to start with a function, 5x squared, and we want to find the derivative of it. So let's set this up. We want to take the derivative of 5x squared. And what our constant rule says is we can take this 5 and we basically move it out of the derivative. So that now we're left with 5 times the derivative of x squared. Well, what's neat is x squared fits our previous power rule. So what this means is now what I can do by the power rule is I can write this as 5, because it's just going to stay there, times the derivative of x squared, which is 2x, because I brought my exponent down with the 2 and I subtracted 1, so I just have 1 there as my exponent. And if I really want to simplify, this means my derivative is just 10x. Now you can go ahead and do the limit process if you want. These rules just help us sort of move a little faster here. But it's really nice because we just applied the constant multiple theorem, we apply the power theorem, and we have our derivative, no muss, no fuss. Let's see a few more examples of this. So next we're given that y is equal to 3 divided by 2x, and we want to find dy dx. So to find dy over dx, that is the derivative, we need to find the derivative of the function 3 over 2x. And the key here is that we need to make it fit the pattern. So the key is we want to rewrite this as 3 halves times 1 over x. Because now we've got the constant times a function pattern. And once we've got the constant function pattern, we can pull that constant out front and then multiply by the derivative of the function that's left inside. And we did this one previously, so we're going to get 3 halves times negative 1 over x squared. And so, by just applying the constant function rule and the power rule, we can get our derivatives pretty quickly. Let's do one more example. So here's our last example from this section. We've got our function g of t equals 5t, and we want to find this quantity. So I want you to take a minute, pause the video maybe, and try to work through what the derivative is here. So hopefully you've thought about it a little bit. You look at this thing and you say, hey, that's not so bad. We've just got a constant out here, so we can just pull that constant out. So let's see, we can write this derivative as now as 5 times the derivative times t. And then, well, what's the derivative of t? Some of you might think that the derivative is 1, but let's look closely here. Our variable is t, but we're taking the derivative with respect to x. So what does this mean? This means x is a variable and t is just a constant. And so we all remember that the derivative of a constant is 0, so the derivative here really is 0. Yes, this was a trick question. I'm not going to apologize for it. I really like this question. I like this question so much, I think I put it on lots of quizzes and exams. So be aware that you always have to make sure that you compare your variable to what you're taking the derivative with. So be careful. The derivative is 0. So what we've done is we've made it to the last theorem from today's lesson, the sum and difference theorems. This is going to give us the power to compute lots and lots of derivatives. It's going to be great. So this says the sum or difference of two differentiable functions f and g is differentiable. That is, if you can take the derivatives of them alone, you can now take the derivatives when you add them. Moreover, we have that the derivatives of f plus g is equal to the derivative of f plus or minus the derivative of g. So the derivative of the sum is equal to the sum of the derivatives. Basically, a way to think about this is adding functions will add together their slopes, right? Derivative is just a big idea of calculating slopes, rates of change, and that's what this theorem says, that you do them independently of each other. So let's look through the theorem to see why this is true with a little proof. So suppose you had to work through this thing using the limit definition. Well, you'd be in for a bit of work, okay? Because if you want to take the derivative of the sum or difference using the limit definition, you need to take f of x plus delta x plus g of x plus delta x minus f of x plus g of x all over delta x. Looks like it's going to be a lot of work. But what we can do is we can do just a little bit of algebraic rearrangement, okay? We can take the g of x plus delta x minus the g of x, move them over here. We can take the f of x terms, move them to the front, break it up into two separate things, because what's nice now is that each one of these things is pretty easy, or at least you should hopefully recognize what this is. This first one is just the derivative of x, or f rather, plus the second one is just the derivative of g with respect to x. So we've got the sums of the derivatives there. So this is really nice. It works out pretty smoothly for sums and differences. So let's go ahead and use everything we've learned today in order to work through some examples. So I encourage you to pause the video, try to work through it on your own, and then compare it to what I get when I work through it. So first we want to compute the derivative with respect to t of the function f of t equals 3t squared plus 1 over t squared. So this means that f prime of t is going to equal the derivative with respect to t of 3t squared plus 1 over t squared. So the first thing I want to do is I want to recognize here that what I have is I have a sum of two functions. Okay, so this means I can break this up into separate derivatives. So this means I need to take the derivative of 3t squared plus, separately, I can take the derivative of 1 over t squared. The next thing to recognize is, well, I'm going to do two things at once. First, I'm going to recognize that I have a 3 in my first derivative. That's a constant, so I can bring that out of the derivative. And in the last one here, I need to do some rewriting. T squared I can also write as t to the negative second. So I'll do that next. So now I brought the 3 out of the front of the first derivative, left with just a really nice t squared in there, plus in the last function after rewriting I have t to the negative 2. And so now what I have is I have really nice power rules I can apply. This first function will be 3 times 2 times t to the first. I brought the exponent down and I subtracted 1. Plus now negative 2 t to the negative 2 minus 1. And after simplifying I have 6t minus 2t to the negative third as my answer for my derivative. So this was really nice. I mean, this was, we had up here a constant rule, a sum difference rule, we have some rewriting stuff to do, another power rule again, so lots and lots of good stuff. So what we want to do is we want to do one more example. So let's go ahead and find the derivative with respect to t of this function here. So I encourage you to pause the video, take a second to think through this. What's the derivative going to be? And now we'll try to compute the derivative of this function. And hopefully what you said was 0. There are no t's up here. Okay? X is just a constant. We're taking the derivative with respect to t. 0. Okay, one more example to actually make an example where you have to do something. So here we have the function j of t is equal to t plus 1 all over t. So we can also write this as t plus 1 over t. And we want to recognize that none of the theorems we've looked at so far in this section apply. We're not taking a sum of two functions. We're not multiplying by a constant. What we're doing is we're dividing these two functions. And so none of our theorems seem to work unless we first take a minute and rewrite this function. So the key is we want to rewrite this function as t over t plus 1 over t. So this is breaking it up from one fraction into two fractions. And this simplifies down to 1 plus 1 over t. Now we have the sum of two functions, so now we can take the derivative. So this means to take the derivative of this function j of t will be the same thing as taking the derivative of 1 plus 1 over t, which breaks up nicely into two different derivatives using our sum theorem. This first one, well, what's the derivative of a constant? Will just give us 0. Plus this second function, even though we've done it before, I'll take the time and rewrite it first as t to the negative first. And now we can use our power rule to write this derivative as negative 1 times t to the negative 1 minus 1, so negative t to the negative second. And for those who really like to rewrite and simplify, negative 1 over t squared. So even though it didn't appear that we could take the derivative of this using our rules, we can. We just have to practice rewriting, breaking things up into sums and differences so that we can finally take their derivatives. So one last idea to get you thinking about later when we come back to derivatives is the idea that linearity has occurred all over. So remember that linearity, we gave this idea that if we have constants in front and we have sums and differences, that we can break up limits by pulling the constants out front, and we can break it up into two separate limits here. We had the same thing happen with integrals. We had these constants that can come out front of our integrals, and we can break up our sums and differences of integrals into two separate integrals. And now we see the same thing happen with derivatives. We break up sums and differences inside derivatives, and these constants all just come out front. So linearity happens all over, with limits, with integrals, with derivatives. It's just a really common thing to see around in math, and it's the same pattern holds over and over again. Constants come out, sums and differences break up, and you compute them separately. but it leads to a really important question. And that question, of course, is what happens when I want to compute the products of things? We saw in the previous example that if we try to take the derivative of t plus 1 all over t, which we could think of as, as a product of two things. We could think of this thing as the product of t plus 1 times t to the negative first. Well, what we actually computed was we computed that this was negative 1 over t squared. And so the question is, does this have anything to do with the product of the functions? Is there a shorter trick we could use or technique rather than just rewriting? And we'll look at this in a few days.